Hi guys, so here we are back with the second part of chapter 12 discussions. I hope we will have another segment after this so that we can nicely split the whole material into three segments of chapter 12, which is kind of a long chapter. However, the material is not that long, like large, I would say. Okay, so you have already learned about um, the parallel axis theorem into the very last slide of chapter 12. Before that, we learned about moment of inertia. And now it's time for us to think about an analogous term or physical quantity of that of the force in linear motion. So we know that in linear motion, if you apply a force, you generate some sort of an acceleration. If there is a net force acting on an object, you get a net acceleration. But what happens in rotational motion? What happens when you have a net angular acceleration working on an object and you want to know what has created that angular acceleration? Okay, so torque measures the effectiveness of the force at causing an object to rotate about a pivot. You can clearly understand that it is no longer just the force itself, right? So it's no longer just the force that this person is applying on the paddle in this direction. There is something else. There is something else which is letting this paddle rotate, and it is, of course, it is related to the magnitude of the force, but that's not everything here. There are some other considerations. So the force will definitely make sure how much this thing is rotating or the paddle is rotating. But there are other things that we will have to consider, and we will combine those different factors into one term called torque. So torque is the effectiveness of the force for which it is rotating. In order to understand this more mathematically or quantitatively, we can think of a geometry where we have like an object, right? This is an object that you are trying to rotate, and it doesn't matter in which direction you want to rotate, but in this case, it is, we are trying to rotate it in this direction. So anti-clockwise direction, okay. So it doesn't really matter, but you will always have to apply a force, or the force will basically generate a torque, okay. Now the torque basically depends on several things. Number one is the amount of the force that you are applying, but also at what angle you're applying this force, okay. So the angle phi is measured counterclockwise from the radial line. That's one of the factors. The force magnitude is the second one. And the third factor is basically where you're applying this force, okay. So if this is the center of rotation, how far from that center of rotation or the axis of rotation you are applying this force. So R. So these are the three quantities on which the torque will depend. These are the quantities on which will decide if the torque is large enough so that this guy can rotate, or it is not significant. These are the quantities which will distinguish between two torques, like more force, less force, more torque and less torque. Okay, so the formula is Rf sine phi, right? So you can actually do this or understand this in many different ways. One way is basically to resolve this force along these two directions. When you do that, you can easily like find the force which is in this direction, and one component of the force is in this direction. And of course, this component will not contribute anything, right? If you push this object towards the center, no way it is going to help you to rotate this guy. The only force that is going to, or the only force component that is going to help you to do this is this guy here. So that's what we have. That's why we have the F sine phi or R sine phi, whichever way you want to call it. It's generally F sine phi, the y component of the force, so to say, if this is your y, okay. However, if this is your y-axis, then it's different. Anyway. So the three things: the magnitude of the force, the distance from the point of application to the pivot, the angle at which the force is applied. These are the three things you will always have to remember. And the unit of torque is just like work done, but it's different, right? It's a different quantity. It's a vector quantity, actually. So Newton times meter. Torque has a sign, just like force has a sign, right? If you apply a force in positive x direction, you call it plus something. If you apply a force in the negative x direction, you write that sign in front of it. Similarly, torque will also have a sign, depending on if it is trying to rotate the object clockwise or anti-clockwise. Okay, so a positive torque tries to rotate the object counterclockwise. And I have to draw this so that you understand it, right? This arrow or this force is trying to rotate this guy in this direction, which is a counterclockwise. So the counterclockwise rotation will give you a positive torque. When you are writing an equation and you need to determine what sign the torque is, you are going to use a positive for this guy. Similarly, this will also be counterclockwise, so positive. This will be a negative one. So this guy is going to give you a negative one. This guy is going to give you a negative one. And these two guys are not basically going to work at all, because this is just pulling this device away from the pivot point, and this is pushing the device towards the pivot point. Both cases, they will basically not contribute to the torque equation. So these are basically zero torques, all right? But all the others, they have a sign, and you can understandably say, right, these two guys have like maximum torques, because this is 90-degree angles, right? And you have seen the torque equation has R sine phi. So the sine of the 90 degree is 1, so that's the maximum value, and that's why for 90-degree forces, you always have maximum torques. As you can see, right? F sine phi. And this is what I was trying to say. So the tangential component, which is this guy, right? You can think of this to be F sine phi, and then you multiply with R, which is the distance. Okay, so if you want to find out for example, the sign of torque here, this is basically a positive sign, right? Because it's going anti-clockwise. You can have multiple torques working on a system, just like multiple forces working on a system. And you remember when we found out net force, we have actually added all the forces algebraically or vectorically, right? So the same thing happens here. If you have multiple forces, you add them like that. If you have multiple torques, right, all these forces are basically generating multiple torques. You can write down them to be as your net torque. And that is the reason, that is the place from where we are starting to develop our second law, Newton's second law for rotational motion. So remember Newton's second law in linear motion, we needed F net, right? In this case, we are going to need a tau net, a net torque to be found out. Now, like every force, right? These are the forces, right? Every force, like every force, gravitational force is just a different kind of force, right? It's just a force. So you can, if you can have torques for all the forces, there is no reason you cannot have a torque for gravitational forces. So for example, if you have an object obliquely placed like this, right? Because of the gravity, it is going to fall down, but there is a likelihood that this is going to also rotate when it is fall down. So basically speaking, you're seeing the effect of torques being generated at these points. I mean, depending on how far you are from the center of mass, right? It is going to rotate and That's the work of um, gravitational torque. And very simply put, gravitational torque is just like any other torques, force times the distance, right? Mg is the force here because it's always down, vertically down. And then if this is the distance, right? If this is the distance along center of mass, then you can call xcm times mg. Okay, so oh, and remember, we didn't use this length. We used this length because we needed the perpendicular length, right? So if you think of the previous diagram, here we go. If you think of the previous diagram, you have to find the perpendicular distance from the pivot to the application of the force. The application of the force here is at this point. The pivot is here. So you can't find out. So this is not a perpendicular, right? If you have to draw a perpendicular, it has to be like this, not this guy. So that's why we needed this length, and that length is basically nothing but xcm. That's why you have a torque to be found in that way. Okay, moving on. Now we have the rotational dynamics, and this we have been talking about for a long time, right? The Newton's second law, tau net equals to alpha times I. This is just like F equals to ma. M is replaced by I. A is replaced by alpha, right? So the net torque causes an object to have angular acceleration. If there is no net torque, then acceleration has got to be zero. So either the object will not rotate at all, or it will rotate with constant angular velocity, just like linear motion. And here is the equivalence that you can see. You have the force replaced by torque, you have the mass replaced by I, moment of inertia, you have acceleration to be replaced by alpha, and then the second law looks like this. There are a couple of problem-solving strategies. There is nothing new here. Again, you are going to work with, just like force diagrams, you're going to work with torque diagrams here as well. I mean, they are essentially force diagrams, nothing different. But you will have to find out the net torque. You will have to find out if the object is accelerating along the rotation or for the rotational axis. And if that is true, then you are going to use this form of the Newton's law instead of the linear form. We are going to stop here, and then for the rest of the remaining of the topics, we are going to come back for the third segment, which is hopefully going to be as short as this one as well. And in that segment, we are going to continue our understanding of torque and angular acceleration so that we can learn a new way of understanding the rolling motion and ropes and pulleys. So I'm going to stop here, and I'll see you in the third segment.